Okay, so towards the end of last class, we began revisiting this notion of dimensionality reduction. So you're basically given a set of data points which all reside in some very high dimensional space, and the goal is to, in some sense, reduce the dimensionality, or in other words, project it down to a set which has a smaller dimension, hopefully where it's easier to work with, and at the same time you don't lose any information. Right? So you want to retain as much information as possible while bringing it down to a vector space of a much smaller dimension so that you can perform all your operations in that dimension instead. Right. And we've already seen one form of or one technique for dimensionality reduction towards the in the first part of the course. We saw the Johnson-Lindenstrauss lemma, where we saw that given any set of n points, n data points residing in some very high dimensional space, there exists a projection down to a subspace of dimension d, which grows something like logarithmically in n, but independent of the dimension of the original data points, such that the pairwise distances are approximately preserved. Right? So there the goal was to find a projection or find a mapping or an embedding down to a lower dimensional space such that pairwise distances are approximately preserved. Right? But now in PCA, or principal component analysis, the objective is a little bit different. There it was just to preserve pairwise distances, whereas here the goal is to project each point in your data set down to a much smaller dimensional space such that the distance between the projections and the original data points are as small as possible. Right? In particular, if 8xi denotes the goal is to find some projection matrix A down to a low dimensional space. Let's assume that the original data points are in R to the capital D, where D is something very, very large. We want to project this down to a much smaller dimensional subspace of dimension little d, where we'll assume that little d is much, much smaller than capital D. So we want to find a projection matrix such that the error, so if you take A times xi, which is a projection of xi down to the lower dimensional space, then norm we want to minimize the sum of the squared errors between the projections and the original data points. Right? And we saw that this is equivalent to maximizing or finding a set of d orthonormal vectors in R to the capital D, which maximizes this particular objective function, which is the sum of the squares of the inner products between the data points and the VJs, the basis for this lower dimensional space. Right? So today we'll see the more commonly used form of PCA and how to derive it. Now the goal, remember, is find a projection matrix A from RD to R little d that minimizes summation I equal to 1 to n norm of AXI minus xi 2 norm square. Right? So firstly, what does a projection matrix look like? So let's say that U1 u2 up to u little d are d orthonormal vectors. In RD, right? What is the projection matrix that takes any vector in R to the capital D down to the subspace that is spanned by these vectors? So this, let's suppose that A is equal to the span of U1 down to UD. Which one? No. Sorry. So okay, the matrix A is capital D cross capital D matrix.
So it should be in R capital D.
That's right. I'm sorry. That's correct. So let's say that A is the span of U1 through UD. Then we want to find the projection, the matrix that projects, or the orthogonal projection of any vector down to this particular span A. So the geometric, so let's suppose that you have some particular subspace and you're given, I'm sorry?
A equal to span U1 UD means what is it? Space of A.
Correct. But then can you give me an explicit form of the projection matrix in terms of the vectors u1, u2, u3 up to ud? So firstly, what is it, like geometrically, what is the orthogonal projection of any vector down to a subspace?
AUI should be equal.
Correct. So that's the definition of any projection, right? So we want A times any, so AUI should be equal to UI. That's true.
Is like sigma UI transpose.
Correct. Or another way to put it is, if this is true, equal to 1 to little d, UI transpose. Also, if I denote the matrix U to have columns U1, U2 up to U little d, right? So this is a capital D by little d matrix. Then A is basically UU transpose, right? So if you had, so suppose that I gave you a vector x in RD, what would be the orthogonal projection of x in terms of the vectors u1, u2 up to ud? So let's visualize this using a picture. So I'm given some vector. So let's say that this is the subspace that I'm interested in. Some subspace spanned by these vectors. And the subspace has some particular basis, which consists of u1, u2 up to u little d. Right? Now I'm given an arbitrary vector that is potentially outside this subspace, and I want to find the projection, the minimum Euclidean distance projection of this vector down to the subspace. All right. So what is the geometric way of projecting it down to the subspace? Yeah? Correct. So basically, you can decompose it as a sum of vectors that lie within the subspace and the complement, and vectors that are orthogonal to vectors in this particular subspace. Right. So in this case, in this little toy example over here, I can consider a basis for R2 as with one vector being the vector that generates the subspace, and another vector that is orthogonal to this particular vector or orthogonal to this particular space. Right? So now how would you find the projection of this vector down to this particular subspace? What is the component along this particular direction equal to? Yeah? It's just the inner product between the vector and this particular basis vector, right? And the basis vector in this direction. I'm assuming that the vectors that I'm considering are orthogonal and normal, right? So then, and so what is the, in general, if I have d vectors, an orthonormal, I have d orthonormal vectors, then what is the projection of x equal to? Yeah, summation I equal to 1 to little d, inner product between the vector x and ud or ui. Right? So this is the magnitude of the projection onto the ith vector times ui. Right? This is basically what it is. Correct? So then I can write this as summation I equal to 1 to d ui times, I have inner product between x and ui, which I can write as x transpose ui or ui transpose x. They're both the same. Right? And just by linearity, this is ui transpose times x, or this times x. Right? And again, since they are orthonormal, this is equal to uu transpose times x. And this is my matrix A. Right? Okay, great. So this is a projection, and my goal is to find a projection that minimizes this particular quantity. Right? If I look at norm I equal to 1 to n axi minus xi square, I can write this as ax minus x Frobenius norm square, where x is basically a D by N matrix. With the data points as the columns, right? So this is the Frobenius norm of A times x minus x the whole square. So A times capital X is ax1, ax2, ax3 up to axn, and therefore the Frobenius norm squared is equal to the sum of the squared errors, right? Okay. So this is equal to u transpose x minus x Frobenius norm square, right? Which is also equal to, so the Frobenius norm square of any matrix is equal to, maybe let me bring this a little later. Let's just take ax. The squared Frobenius norm is of a matrix, let's say B, is equal to the trace of BP transpose or B transpose B. They're both the same, right? So let me use that fact over here. This is trace of ax minus x minus x this is equal to the trace of a x transpose x minus 2 times x this is x transpose ax minus 2 times ax x transpose plus x transpose x. Basically, I have minus ax x transpose minus minus ax whole transpose times x, which I've just written as ax x transpose, right? And what is A transpose A equal to? Yeah? Why? Correct. I'm sorry? So U is a matrix with orthonormal columns, right? So what is this equal to? Can you look at it a little more carefully? Why scalar value? So what is, okay, so U is a matrix with orthonormal columns, right? What is A transpose? If A is equal to U transpose, then what is A transpose A equal to? U transpose U transpose, right? What can you say about U transpose U? It's I, right? But what about U transpose?
Orthonormal U transpose U equal to U.
No, right? So remember that U is capital D by little d matrix. So this is identity.
The entire C no.
I'm sorry?
E transpose is equal to A.
Why? Why is A transpose equal to A? Correct, yeah. So this should have been A.
And A square is equal to A again.
A square is equal to A, yes. So I think I missed this. Transpose. Right. So this is U transpose, right? So this is equal to U transpose, which is A. Since it's a projection of a projected vector is the projected vector itself, right? So this is equal to trace of X transpose AX minus 2AXX transpose plus X transpose X. This is equal to, well, trace of AB is the same as the trace of B times A. So this is AXX transpose minus 2AXX transpose plus X transpose X. Minus AXX transpose plus X transpose X, right? So minimizing the left hand side, squared Frobenius norm is the same as minimizing the trace of X transpose X minus AXX transpose. The trace of a sum of matrices is the sum of the trace, and the first matrix is independent of A, independent of U. right? So this is equivalent to maximizing AXX transpose or over U trace of UU transpose XX transpose X transpose U. Right? This is also equal to little d UI XX transpose UI. Right? And for what vectors is this U maximized? Correct. So it's equal to, so the right hand side is maximized when you choose U to be eigenvectors, U1, U2 up to UD, to be eigenvectors corresponding to the D largest eigenvalues. Note that the matrix in question, XX transpose, this is a matrix that is symmetric and positive semi-definite. So all of the eigenvalues are guaranteed to be greater than, or they're real, and in fact they're all greater than or equal to 0. Right? If you've not seen the proof before, I would encourage you to try and prove this. And one hint to prove this is you can use the spectral theorem to say that XX transpose can be written as summation I equal to 1 to capital D lambda I VI transpose, where the VI's are orthonormal eigenvectors corresponding to the eigenvalues lambda I. Right? So the V1 up to V capital D, they form an orthonormal basis for RD. Now if you express the ui's in terms of the vi's as a linear combination of the vi's, then you maximize, you'll get the same thing, that the maximum is achieved when u1 through ud is equal to v1 through vd. Right? So essentially, finding PCA corresponds to finding the top k eigenvectors or the top little d eigenvectors for the matrix XX transpose. All right, but in practice, this many a time this is not done. You don't find the eigenvectors of XX transpose. You do it a little bit differently. But before we go to that, let's see what is the complexity of computing or finding the PCA for a given set of data points. All right. So to find PCA, you need to first compute the matrix XX transpose. How many operations does that require? Yeah? Y n square? Yeah, n d square, right? There are n data points. Each vector is a vector of length capital D. So this requires d square n, order d square n number of arithmetic operations, right? And then you need to find the eigen decomposition. What's the complexity of finding the eigen decomposition? Yeah, the best algorithms do it in time order d cube, right? Which could potentially be fairly large, because if the dimensionality is too large, then particularly if, let's say, capital D is comparable or larger than n, this could be pretty expensive, right? This will be more relevant when we want to do kernel PCA, where the dimensionality can be arbitrarily large. All right. So another way of doing this is, instead of looking at XX transpose, you look at XX transpose X. All right. So let's suppose that U1 up to U, say capital D, eigenvectors, let's just take U little d because that's enough for us, of XX transpose. Okay. Now I claim that X times Ui is an eigenvector of let's say something else. Let's say that V1 through Vd are eigenvectors of X transpose X, all right, corresponding to the eigenvalues lambda 1 up to lambda d. So lambda 1 up to lambda d are some arbitrary eigenvalues, all right. They don't necessarily have to be the top d eigenvalues, but that's what we're really interested in, all right. And let's say that V1, V2 up to Vd are the eigenvectors corresponding to these d eigenvalues, all right. Now one thing to note is that X transpose X and XX transpose, they both have the same set of non-zero eigenvalues, right? In fact, they have the same set of eigenvalues up to multiplicity, right? Because the dimensionality can be different. One of them, x transpose or x transpose x, is going to have a lot of zero eigenvalues.
Transpose is d cross small d cross matrix. So we
In
try
this,
to come instead of
no. X is d by n, capital D by n, right? Little d has not come into the picture in x transpose x or x transpose, right? And you're right. That's what I'm heading towards. So x transpose x is an n by n matrix, right? So instead of my complexity being dominated by capital D, it's going to be dominated by n.
trying to come up with the small d representation.
You want a small d representation anyway, but this will have some other benefits, as we'll see. Okay. So this x transpose x is basically our Gram matrix, right? So x transpose x is basically the matrix of all possible inner products between xi and xj, right? And recall that if we want to use the kernel trick, we want to represent everything using inner products. As long as we can express the whole problem as having to do purely with inner products between data points, we can use the kernel trick to sort of look at the higher dimensional embedding. All right. Okay. Anyway, that aside, suppose that V1 through Vd are eigenvectors that correspond to lambda 1 through lambda d, but for the matrix x transpose x, then what can we say about x times Vi, right? So let me take x times Vi and multiply this by x transpose. Okay. This is equal to x times x transpose x times Vi, which is nothing but lambda I times xvi. So if Vi is an eigenvector of x transpose x corresponding to the eigenvalue lambda I, then xvi is also an eigenvector, but for the matrix xx transpose and corresponding to the same eigenvalue lambda I. All right. So now that's number one. So xvi is an eigenvector corresponding to lambda I for the matrix xx transpose. Okay. And what about if I take any I comma j for I not equal to j? Suppose that V1 through Vd are orthonormal. What about xvi transpose xvj? So you take two different eigenvectors, xvi and xvj. What can I say about this? This is equal to Vi transpose x transpose x Vj. All right. But Vj is an eigenvector of x transpose x, right? By definition, corresponding to the eigenvalue lambda j. So this is equal to lambda j times Vi transpose Vj, but Vi and Vj are orthogonal to each other. So this is equal to 0 for I not equal to j. All right. So this, let me. This is something a little more important here. this is equal to 0 if I is not equal to j. But what happens when I is equal to j? This is equal to lambda j, right? Or lambda I, whatever. And in that case, where I is equal to j, the left hand side is just the norm squared of XVI, right? So norm XVI square, this is equal to lambda I. So the norm of XVI is square root of lambda I. So now if I want an orthonormal basis or an orthogonal set of eigenvectors for x transpose from the corresponding orthonormal set of vectors for x transpose x, then all I need to do is take the following set: xv1 by root lambda 1, xv2 by root lambda 2, xvd divided by root lambda. All right, so this is basically the same as u1 up to ud. So I can get u1 up to ud by taking an eigen decomposition of the Gram matrix x transpose x, keeping only the top d eigenvalues and eigenvectors, and then computing xv1 by root lambda 1, xv2 by root lambda 2 up to xvd by root lambda d. But now what is the complexity? So first you need to compute x transpose x. What is the complexity? N square d, right? It's order n square d, because x transpose x is an n by n matrix, and then I need to do an eigen decomposition followed by multiplying by xv1 x multiple times, but that's still order nq. So the overall complexity is just order n cube plus order n square d, whereas previously it was order d square n and order d cube. So when d is much larger than n, this is obviously beneficial. This also helps us if we want to do PCA not in the ambient space but rather in the kernel space, right? So now suppose that instead of doing PCA, so let's say that psi is an embedding from Rd to some Hilbert space, right? This could be of any dimension. I don't know what is the dimension of this Hilbert space. And suppose that H, for now, just for conceptually, suppose that this is finite dimensional. Then I compute let's suppose that psi x is the matrix psi of x1 up to psi of xn. Okay. So now if I want to compute psi x transpose, right? So if I wanted to do PCA over this in the Hilbert space H rather than RD, then basically I would have to construct psi x transpose and then find the top D eigenvectors corresponding to this. But I can't, but that's highly complicated because I would need to compute the embedding first, embedding of all of the points, which could be, for one, computationally complex, and two, if I don't have the explicit form of psi, then I can't really do it at all, right? So instead, what I could do is compute psi x transpose psi x, which is what? So it's basically the matrix of inner products between psi x1, psi x1, psi x2, psi x1, psi x2, and so on, right? But each psi xi inner product between psi of xi and psi of xj is just k of xi xj. So this is nothing but a matrix k of x1 x1, k of x1 x2, and so on, right? This is just the Gram matrix. So I can now do the eigen decomposition of the Gram matrix and get the corresponding eigenvectors. So say v1 up to vd are top D eigenvectors of G. Okay. Now, if I'm given a new point, right? I want some x, and I want the projection down to this particular point. The representation would be psi of x times let's see, D eigenvectors of G, psi of x times the projection matrix, which is my A, right? So this is what I, in some sense, want to compute. But then this is my UI is psi x times Vi divided by root lambda I. right, where this psi x is an n by D matrix. D, I'm sorry, should be, it's an n by n matrix. Okay, my bad. This is whatever. The dimensionality, say D prime by n. Right? So if I want to express, let's say, x, an arbitrary vector x, the projection is going to be, basically what I want to compute is inner product between or x comma ui times ui. Right? This is the approximation of x in the lower dimensional space. Right? This is equivalent to just storing inner product between x u1 up to x ud. But the problem is that I really can't compute ui directly. And the reason why I can't compute ui directly is because this is in the high dimensional feature space. All right? But the advantage is that I can compute these inner products easily. All right? In fact, maybe this is a little misleading because the UIs are in the high dimensional feature space. I should really say the inner product between psi of x and u1 psi of x u2 up to psi of x ud. Right, so this is the low dimensional approximation of a given vector x, a new vector x. All right. But since this can be expressed as a collection of inner products, I can compute this easily. Psi of x comma ui is nothing but the inner product between psi of x and the matrix psi x vi by root lambda I, which is again, if you remember what psi x was, right? Psi x is basically this vector, this matrix over here. So this is psi of x transpose psi x1 psi x2 up to psi xd times vi by root lambda I, which is this matrix inner product between psi of x, psi of x1 up to psi of x, psi of xd times vi by root lambda I k of x x1 k x x2 up to kx xd times vi by root lambda I. Alright, so the procedure to do kernel PCA is the following. So first you construct the gram matrix K xi xj for all pairs, the matrix, the gram matrix. And the next step is you find the top d eigenvalues and eigenvectors. Lambda n. So you just compute, enough to compute lambda 1 up to lambda d and the corresponding eigenvectors v1 up to vd. And you basically store this as well as all of the n points, n data points that you have. So given a new point, x, this particular point is embedded into a d-dimensional vector where each, let's say alpha 1 up to alpha d, this is the low dimensional representation of x, and this alpha 1 through alpha d, so each alpha I is basically kx x1 up to kx xd times vi divided by root lambda I. But one thing to be noted is that when you're doing kernel PCA, you're not minimizing the Euclidean distance between the vector and its low dimensional representation in the domain. This is the closest, you're minimizing Euclidean distances not in the domain but rather in the feature space. So all you're guaranteed is that the sum of the squared errors in the feature space is minimized, not in the domain. Okay, and therefore, if you don't choose your kernel or the embedding carefully enough, kernel PCA is not guaranteed to give you good performance. So a lot of times kernel PCA fails because you didn't choose the right kernel, which doesn't happen so much with PCA because as long as you choose D large enough, you're guaranteed that what you get is going to be a reasonably faithful representation of the original data point. All right. So it's not a linear projection. this embedding or into this lower dimensional space is not linear. And in kernel PCA, I mean, if you think about it, we're first embedding the vectors in a higher dimensional space and then projecting it down to a lower dimensional space. I'm sorry? I wouldn't go so far to say that it's equivalent, because we're using a very specific form here. We're using PCA in the higher dimensional space. So one other point that I want to add is that typically in practice, PCA is done by first centering all of the data points. Right? Although whatever I've said so far it doesn't really matter what the data points are. Right? They may or may not be centered. In practice, we first center the data points x1 through xd. So basically you just compute the mean, which is 1 over n, so x1 through xn, summation I equal to 1 to n xi, and then you look at x1 minus mu, x2 minus mu, and so on up to xn minus mu. And then you do PCA on these vectors. The reason why the centering is done is, for one, it performs pretty well in practice. And the other is that it also has an interpretation in terms of the direction along which the variation is maximum. All right, so if you think of all of the data points being centered, let's suppose that we have already centered the data points, then, and you have a collection of data points that look like this. Intuitively, it would seem that this what PCA should do is project all of the points down to this particular subspace, right? Because I mean, if you look at it, for example, if you compare this subspace versus this subspace, it's intuitive that the sum of squared errors would be lower for this particular subspace than for this particular subspace. At least that's visually obvious. But you also see that along this direction, the variation in the data is more compared to what is happening along this particular subspace. So once you center things, this is the subspace that has the largest variance. That's the interpretation. And in practice, this seems to work very well. Now you can do this for standard PCA, but it doesn't work for kernel PCA anymore, because after all, you're taking the means, you have to take this in the space where in the feature space, right? When you're doing kernel PCA, which is not possible anymore. But what you can instead do is you take K prime, or say G prime, which is equal to G, the gram matrix, minus this matrix 1n. I'll define what this is. G minus G 1n plus 1n G 1n, where this matrix is just 1 by n times the all ones matrix. I'll leave it to you to verify that. Okay, so if we go back to the PCA with centered vectors, right? In this case, the gram matrix is just correction of inner products x1, x1 up to x1, xn, xn, x1, xn, xn. If all of these xi's are centered, right, that is the sum of all of the xi's is equal to 0, then what can you say about any row sum or any column sum of this gram matrix G? So every row and every column sums to 0, because if you sum any row, so let's say I sum the ith row, it's basically equal to summation inner product between xi and xj, where you sum over all possible j, which is the same as inner product between xi and sum over all j xj, which is equal to 0. Right? So I leave it to verify that for any gram matrix G, so G must be symmetric. Every row column of G prime sums to 0. Any questions? Okay, so I'll spend the next, let's say, 10-15 minutes talking about a different form of dimensionality reduction. So far, we've approached dimensionality reduction in a couple of different ways, right? Right, the first is the case where we wanted, so given x1 through xn, want to preserve or approximately preserve pairwise distances. All right, and this is only for this point. Let's say you add a new point to this particular data set, then you don't guarantee anything else. In some sense, this is useful for, let's say, storing the data set, such that you want all the operations that you want to do later on are in terms of Euclidean distances between the points. Or let's say you want to do clustering for these particular points. All right. The second approach that we took was PCA, where given a particular data set which captures some information about the ground truth. We wanted some kind of a projection or embedding down to a lower dimensional space, such that the objective function in this case was that xi minus xi prime square was small. All right, but at the same time we want to use this to capture some important features of the data, so that if we get a new data point which is not within this particular data set but has the same, loosely speaking, features of this particular data set, then you should be able to project that down as well to this low dimensional space using this embedding, and at the same time without losing useful information about the data. All right. There's another approach where you assume that you already know something about the data. You know something about the structure of the data, and you still want to bring it down. So we'll assume that X belongs to some set S where this set is known to us. Okay? And want to again reduce the dimension such that we can at least approximately recover X from X prime. So in some sense this is like traditional compression. So you want to compress X to give X prime such that whenever you want, now this X prime has much smaller dimension than X, but if you want to do so, there's a way of going back to X from X prime, or at least approximately in some sense. All right. So let's see one concrete scenario for this. We'll assume that the data that you get is sparse. Let's say little s sparse vectors in RD. All right, so this whole area goes broadly by the name compressed sensing. So once again, the goal is to find a particular matrix A such that we will demand something even stronger this time. You can recover any X in S, any S sparse vector from A times X. All right. So let's step back and think about this problem a little bit. Suppose that little d is equal to capital D. Okay, you didn't really demand any sort of compression. Then you could potentially just choose A to be any invertible matrix. Then obviously you can recover X from A times X. All right. Now suppose that you didn't have that. Okay. Then essentially you're given A times X, you're given some Y, and you want to solve for Ax equal to 1. You're given Y, which was obtained by projecting a sparse vector down to a little d dimensional space, and you want to solve for Ax equal to Y. Now we have fewer equations than unknowns. But the advantage here is that you know that it is S sparse, that the original vector x is S sparse. Does this make it any easier? And in particular, how small can D be? Suppose that S is something very, very small, but capital D is very, very large. Then how small can little d be? Okay. It turns out that we can make little d to grow as order S times log which can potentially be huge savings, right? Let's say that capital D is, let's say, 1 million or 10 million, and S is a few hundred. You know that just a few hundred of these entries are non-zero. The non-zero entries can be arbitrary, by the way. All right, I don't say that they have to be 0 or they have to be 1 or -1, nothing, no restrictions. But only S of those entries are non-zero. The remaining capital D minus S entries are all equal to 0. Okay? So if S is something that's very small, you can get a huge savings in dimension going from capital D to log of capital D, essentially. Right? And moreover, our requirement is very strict at this point. We want to be able to recover X exactly, not approximately. Okay, so it's indeed surprising that this is even possible. Right? Just knowing the fact that the vector is sparse means that you can get rid of a lot of information. Remember that if suppose that someone told you which of the locations were non-zero, right? There's some side information which tells you which locations are non-zero. Just storing the non-zero locations requires space order S. Right? You can't do any better than that. But what this is saying is that with a multiplicative overhead of log D, you can recover S. Even you can also encode this positional information, so to speak. All right. And okay, so another way to sort of see this is, suppose your goal was just to store this. Okay, you know that there are S locations which are non-zero out of D possible locations. What would be the optimal way of storing the entire vector, where you assume that S is much, much smaller than D? Any thoughts? Your goal is to only store it, okay? No, I don't require you to be able to do A times X or anything of that sort. Any nonlinear operation, you just want to store this vector. So given, let's say, X in RD with S non-zero entries, how much space is required to store this? Assume that each real value can be represented using some constant number of bits.
S multiplied by C plus log 2D.
Why log 2D? One strategy is there are S. So can you repeat what you just said?
Each non-zero entry, I will store
Correct.
the non-zero entry alongside the index in the vector.
Correct.
This
So
I will do for all the non-zero entries.
correct.
So since the number itself can be of C bits, while the index can be of maximum log 2 D bits, because D is the number of the index can be.
Okay, you mean log to base 2 of D.
Yes.
Okay, fine. Yes, that's right.
Why this will be maximum S time, the number of entries times.
Correct. So basically one approach is you store the locations of the S non-zero entries and then store the values of the S non-zero entries. You separate these two out, right? So you need to store S real numbers and S locations. Right. So you form a table with n rows where you have the location and the entry. All right. Now to store each entry, you need some constant number of bits, right? Because it's a real value. We're assuming that you can represent it using a constant number of bits. And to store each location, I need order log d bits, right? So the total space that is required is order s log d. Right? And basically, this is saying that the same can be obtained using a linear transformation. Right? This process guarantees that you can recover x back from this representation. And this says that a linear compressor also achieves the same thing. Now, these constants involved could be different, right? But nevertheless, you're still getting up to a universal constant. You're getting the same compression. All right? But then this comes with other advantages because all the advantages that a linear transformation can provide you. In the sense that distances you can also have, let's say, approximate distances being pairwise distances being preserved, and so on and so forth. Okay. So maybe let's stop here. If A is a rotation matrix, I agree, but we can say something more. I'll talk more about that in the next class. Yeah, approximately I want this to be the same. Right? Okay, so let's stop here.